Okay, so we were continuing with the concept of convolution, and this was slide set number 4 that we had already started, and we talked about some basic concepts. If there are any questions, please go ahead. If there are no questions, I will just continue from the slide set number 4 as I mentioned. Okay, so the two concepts that were important for the convolution, let me just go through them. The two concepts were one related to this impulse response, that what is an impulse response. So impulse response is what comes out if you give an impulse as an input. That's the impulse response, and we call it h of n. And the second thing that we need to know was that we can express any discrete time signal in terms of sum of scaled delayed impulses. So based on these two concepts or knowledge of these two things, we came up with the concept of convolution. So the concept was quite straightforward, that if we have a particular discrete time system where x of n is the input and y of n is the output, and we know that it's a linear time invariant system, it's a discrete time system, then we know that if we give delta n as an input and the output that comes out, we will call that h of n. And this h of n can be a single impulse, can be finite number of impulses, or can be infinite number of impulses. So because it is a LTI system, we know that if we give any scaled version of the same impulse as an input, the output that will come out will be the scaled version of the impulse response. Similarly, if we just give a delayed version of impulse n minus any value k, the output will be a delayed version of impulse response. And if we give any, let's say, scaling factor with this, the output will also get scaled accordingly. And if we have multiple of these impulses, in general, if we have multiple of these impulses, so let me again do the same thing which I was doing earlier. The concept is that if we give scaled delayed impulse as an input to a system, and if we give multiple of these scaled delayed inputs as an input, then what do we get? The result would be y of n, which would be sum of scale delayed impulse responses. So this is the whole theory base or concept of convolution. So sum of scale delayed impulses, giving you sum of scale delayed impulse responses as an output. This is the concept of convolution. And the summation that you see on the right hand side, we call that as convolution sum. So this thing here is known as convolution sum. And we have a symbol for that. We just put a symbol of star in between, and that is the symbol of convolution. X of n convolved with h of n. So this was the theory base that we covered last time. And here again, the same things are covered in the next few slides. So if you see here, we can represent x of n in terms of sum of scale delayed impulses. You can either write it as a summation, or you can just expand it and write the summation in this particular shape. So sum of scale delayed impulses will end up giving you. So this is what the concept of sum of scale delayed impulses is, that any discrete time signal x of n can be considered as sum of scale delayed impulses. And if we give sum of scale delayed impulses as an input, the output will be sum of scale delayed impulse responses. So here is an example where an x of n is given to you, and we have multiple of these impulses present in x of n. So we can just take these impulses separately, and then we can see response for individual impulses, and finally we can just add up all the responses together and we'll get your output. So delta n giving you h of n, impulse giving you impulse response. And the impulse response that we get here are basically examples of three types of systems. In one system, we give a single impulse, and the output that came out, the impulse response, we see three impulses. So we call this type of thing as finite impulse response system. You give a single impulse, the impulse response that you get has got a finite number of impulses. Here we see specifically three impulses result. So if the result of an impulse, the response that we get is a finite number of impulses or countable number of impulses, then we say we have a FIR or finite impulse response system. And just looking at the equation, if you see, this is the difference equation. And difference equation we know is the equation which gives you relationship between input and output. In the difference equation, to compute or find out y of n, if you require just feed forward terms, just x terms, there is no feedback, there is no y n minus or n plus any term present here, then we say that we have a feed forward system. We have a feed forward system, and this will result in a countable number of impulses if you give a single impulse as an input. This is an FIR system. Similarly, if you see this second example, here to compute y of n, we need x of n and the previous output y of n minus 1. So this is basically the feedback term that we have. So even if a single feedback term is present or more than one feedback terms are present in your difference equation, then you will end up getting a infinite impulse response for that system. So if you give a single impulse to this system, the output that will come out will be not the countable number of impulses, it will be a whole series of impulses. In this particular case, we see that we have got a decaying sort of a set series of impulses, and they will go on and on and on all the way to infinity. So this is a infinite impulse response system. The third example also has got a feedback term right here in your difference equation. So even if you have a single feedback term, the response that you will get would be, or a single impulse response you will get would be infinite set of impulses. In this particular case, the set of impulses tend to just increase or grow with time. So this is decaying, this is growing. And again, whether it decays or whether it grows will depend on whatever coefficient you have here. But you become an expert of just seeing the equation and judging that how it will respond by the time you finish your DSP. Right now, we are just introducing two categories, one FIR system, the other IAR system. And this IR that you see is basically the impulse response. Okay. Now, if you give a whole series of scale delayed impulses as an input, the output that you will get would be the convolution sum, as we call it. The output would be y of n, which will be sum of scale delayed impulse responses. So same scaling factor, and instead of delta, you will end up getting h n minus k. So this is what will result if we give this input. So sum of scale delayed impulses giving you sum of scale delayed impulse responses, and this sum of scale delayed impulse responses is also known as the convolution sum. As I mentioned, this old convention of writing it this way is not right. We tend to write this whole thing in this particular pattern, right? Okay, here is another example of a system which is taking x of n as an input, and we can just judge what the output will be. And I kind of skipped this example, not a very good example to follow. And this is basically the more conventional way of writing your convolution sum. And we have a symbol for convolution. This is what we covered last time also, that if you give x of n as an input to any system whose impulse response is known, we can find out the output just by convolving x of n with h of n. And this is the symbol for convolution. And what does convolving mean? It means convolution sum. It means this summation that you see right here. So this star symbol actually means this convolution sum. So this is what we covered last time also. I'm just quickly going over it. Next, system identification and prediction. So we can completely identify or completely specify a system by two methods or by two means. One mean is by knowing the difference equation. So if difference equation is known, Then, just like you see right here, if difference equation is known, then we can just have any particular input, plug in the value of that input, and you will get the value of your output. That is one way. The second way is, if you know your impulse response, if we just give delta n as an input and we just record or find out whatever the output is, whatever is the impulse response, then that also is good enough to find out how the system will respond for any given input, and that is by using the convolution sum. And this is another example where we are given h of n, it is known for the system, we are given x of n, and using these two, we can just find out what is the output, and output would be y of n would be simply convolution of x of n with h of n. And what does this convolution mean? It means convolution sum. Sum of k equal to minus infinity to infinity, x of k, h of n minus k. Now, once we open this summation up, you will end up getting all these terms. And then we will see that the values we can just plug in for all the terms and end up getting the value right here, and you will end up getting the answer. Now, I think last time also I explained that there is a problem with the examples which are given in the book or in the slide sets, because they are directly taken from the book. These slides are taken from the book. The problem in these examples are that it doesn't really clearly tell you the h of n index. We don't know the index starting point, because typically if you see this type of thing, it is assumed that this first index is for n equal to 0, then n equal to 1, n equal to 2. This is what it implies. But here if you see h of n, the plot that we have here, the first 0 is for n equal to minus 2. The second index is for n equal to minus 1, and n equal to 0, 1, 2, and 3. So how do we really find out that what is the starting index? Two methods I told you. One method was that we put the starting index value right under the square bracket, which is an old convention, no longer followed, but still in some old text you may come across this, or some old sites may refer to this. But more recent convention is that we actually put an arrowhead in where the index is 0. So here if you see, we have 0, 0, and that 1. 1 is for n equal to 0. The 0, 0, and 1. This is where n is equal to 0. We put an arrowhead right here, a small arrowhead just under this one. This specifies that this indexing is such that n is equal to 0 here.
Excuse me, sir.
2 and 3, 4. Yes.
So ये वाली बात repeat कर सकते हैं?
Okay. Basically just giving you a convention. If we are given, let's say, x of n is equal to 1, 2, and 3. If you're just given this, no other qualifying statement, no diagram, nothing, then this actually means that this indexing starts from n equal to 0. And if you just plot it, this actually means this, that you have 1 here, and then you have 2 here, and then you have 3 here. This is for n is equal to 0, 1, and 2. This is what this thing without any qualification actually means. But if we have another situation where we are given a diagram, let's say, and we are given a diagram which actually shows that, let's say, 1, 2, 1, 2. If this was, let's say, another example, and this figure was given to you that this is x of n, and if you want to write it just like this, a set of numbers, this is n and this is for minus 2, minus 1, 0, and 1. If you have this type of a situation given, then how do we write your x of n? If we write our x of n as just this, 1, 2, 1, and 2, this creates confusion, because this tends to show that this first value is for n is equal to 0, but we know that this first value is occurring at n equal to minus 2. Now how do we actually specify this thing right here? One method is that we draw a sort of a table and write it like this, that x of n, and here we have n, and we have, let's say, 1, 2, 1, 2, and we have indexing shown. If This is a much nicer way of expressing, let's say at -2, -1, 0 and 1. So if this table is given, fine. But if you just want to write it like this, then how do we specify the index? And that is specified by two methods. One, I told you, the old method, which I still refer to because some old books refer to this. Here we just put a small value just under the square bracket. This actually shows us that this first index is for n is equal to -2. And then -1, 0, 1 and 2. It will continue like that. The other more recent convention is we just write this as, let's say, 1, 2, 1, 2, and we put an arrowhead where your n is equal to 0 is. We put an arrowhead like here, small arrow like this. This you will find, this convention you will find in more recent books which you come across, or more recent sites that you come across. Now the same number I can write it like this also. X of n is equal to, let's say, 0, 0, 1, 2, 1, 2. And we put arrowhead right there. There is no difference between this and this and this. They are one and the same thing, just different ways of writing the same thing. So either we can specify it as a table, we can write it like this with indexing right here, we can write it with an arrowhead right there, or we can just write it in any particular shifted form, but arrowhead specifying the index value, or a diagram can be given which actually clarifies that how those signal impulses are located. So is that clear here? Any confusions in this convention? It's very straightforward convention.
Yes, sir.
And okay, and throughout this course I will be mostly referring to convention which is more recent, which is this convention. And if you don't see anything mentioned, if just this type of a thing is given to you, and then it means that first index is 0. So this is more recent convention, and that is what I was referring to. Okay, so in this example, as I mentioned, I just kind of skip these examples and give my own examples. Reason being, people get confused because we don't see that arrowhead right here. X of n, if you see, this is x of n. They write the numbers, but they specify the location in shape of a graph or visually. So if you see here, this actually value of 0.5 starts at n equal to 0, and before that these zeros are at -1 and -2. So either again we can put a -2 here, or we can put a arrowhead right here. So two ways in which we can do this. So if I have to give this example, I would simply write h of n, which is more appropriate as 1, 1 and 1, and I would have written x of n as simply 0.5 and 2. So this is how I would have written it, because we don't need to put zeros here, we don't need to put any particular conditioning or diagram. If you have written it like that, and if you plot it, it will end up coming out to be like this, 1, 1, 1 and then 0.5 and 1. So let's solve this particular example in our own way. So if we are given the same example, let's say x of n given and h of n given, and in this example h of n is given as 1, 1 and 1, and x of n is given as 0.5 and 2, I believe. Is that right? So if we are given this, and we have to find, let's say, y of n. Y of n, again, two methods we saw last time. One method is that we take x of n in terms of impulses. We just write it as 0.5 delta n, and we write this other value as 2 times delta n minus 1. We can write it like this, and then see that delta n gives this, 0.5 delta n will give 0.5 times this, and delta n minus 1 will give shifted version. If you shift it, it will become 0, 1, 1, 1, and 2 times that will become 0, 2, 2 and 2, and we add up your impulse responses and it will give you your answer. So that method is basically the graphical method. But if you want to just stick to, let's say, pure mathematical way without any graphical representation, then we will do it like this. We just say that the output is just convolution of x of n with h of n, and convolution means convolution sum, k equal to minus infinity to infinity, x of k, h of n minus k. right? And then we open up this. Now, what should be the limits for this k? I talked about this earlier also. It will depend on this scaling factor x of k. So wherever we have the non-zero values, we are interested in that. And before that or after the signal dies down, we are not interested in those values. If you see this x of n, it is valid for n is equal to 0 and n is equal to 1. If it was x of k, it will be valid for k equal to 0 and k equal to 1. And all the values of k before 0 and all the values of k after 1 are all zeros. So the limit of k would be k equal to 0 to 1 x of k h of n minus k. And then we can just open this up. It becomes x of 0 h of n minus 0 and plus x of 1 h of n minus 1. So this thing we can just plug in the values. X of 0, this is x of 0, it is 0.5, 0.5, and h of n, this is h of n, it is just 1, 1 and 1, and plus your x of 1 is 2 and h of n minus 1 is this thing shifted right by 1. If you shift it right by 1, it will become 0, 1, 1 and 1. This is h of n minus 1, h of n shifted right by 1 unit. So we can just add them up together. You will end up getting 0.5, 0.5, 0.5 plus the second part will become 0, 2, 2 and 2. So if you add them together, this will end up giving you your answer, which will be 0.5, 2.5, 2.5 and 2. So this will be your simple y of n. So we can just use simple mathematics and find out the answer. So if we see it right here, this is exactly what they have done, and answer is still 0.5, 2.5, 2.5 and 2, but they have not actually put an arrowhead right here. It actually starts from right there. So this will be your y of n. So this example you can just go through yourself also. The confusion part which actually should have been clarified in the example is that they should have put an arrowhead right there, or it would have been much simpler if they had specified h of n as this or x of n as this, and then y of n would be simply this, and we can just plug in the values and get the same answer. Okay, so multiple different examples can be seen for the same convolution. Now one thing I just skipped right here was we can completely specify or identify your system if we are given either the difference equation, just like here, or we are given the impulse response. Now for FIR system, there is a direct one-to-one relationship between impulse response and difference equation. Given one, we can find the other. Typically we are given difference equation, and from difference equation it is very easy to just come up with your impulse response. If you have a FIR system, that means you have a difference equation which does not have any feedback term. If that is the case, then you will see here that instead of x of n, we will just replace it with delta n, and we will just replace all these values and see that what do we come up with. So if input x of n becomes delta n, then x of n minus 1 will become delta n minus 1. So typically we are just replacing x with delta actually here, and this x of n minus 2 will become delta n minus 2. And if x of n becomes delta n, output y of n actually becomes h of n. So we just replace x with delta and end up getting your impulse response. So this is delta 0.5 delta n minus 1, 0.25 delta n minus 2. Either we can write it like this, or we can write it like this also. It will be just 1, 0.5 and 0.25. We can write it like this also, or you can just draw your h of n, and the diagram will be something like this. We have 1, and then we have 0.5, and then we have 0.25. So this is your 0, 1, 2, this is your n. So we can directly find your h of n. You can directly find your h of n given your y of n. And either of these, if available to us, a difference equation or impulse response, any one of them is good enough to completely identify your system or completely predict your system. And that given, any one of them is given, then we can find out output for any given input. I'm sorry for this. Okay, any questions here? So basic concept of convolution we covered, some simple examples we covered. Now let's try to go over more complicated example. Let me give you one more complicated example which will further explain your convolution part. Let's say we are given diagrammatically x of n has 2, 1 and 2. This is -1, 0 and 1. This is your x of n given, and diagrammatically we are given h of n. H of n is also given to us as, let's say, 1, 1, 0 and 1, -2, 1, 0 and 1. If we are given these two, we are given x of n and we are given impulse response h of n for a system. And the question is to find out what is your y of n. So how do we solve it? Let me solve it and show you. So this is the case and we have to find your y of n. Then how do we proceed? First of all, let's just try to write x of n in terms of any particular nice way. So if we write it as 2, 1 and 2, then we'll put a small arrowhead right here. And if we write your h of n, it will be written as 1, 1, 0 and 1, and put a small arrowhead right there. So if you have to find y of n, that y of n would be actually equal to x of n convolved with h of n, right? And convolution actually means convolution sum. This is k equal to -infinity to infinity x of k h of n minus k, right? So now this x of k, as I mentioned, we can use to specify our limits. Here we can see x of n indexing starting from n equal to -1 going to 1. So x of k also indexing of k would be from -1 to 1. Before this and after this all the values are 0, so it doesn't matter to us. So we can just write it as k equal to -1 to 1 x of k h of n minus k, and then we'll just open this up. So this will become x of 0, so x of -1 h of n minus -1 makes it x n plus 1, plus it will become x of 0 h of n minus 0, which is h of n, plus x of 1 h of n minus 1, right? And then we can just plug in the values here. So the values that you will get would be what? So x of -1 is 2, and h of n plus 1, this is h of n. H of n plus 1 is this thing shifted left. So h of n plus 1 would be this thing shifted left, and if you shift it left, it will become 1, 1, 0, 1, and this arrowhead will come right here. So this thing, if you just shift the whole figure left, then indexing will start from -3, and we have 1 and then 0, and then 1 right there. Although we can put a 0 if wanted, doesn't if you don't want to, it's up to you. So we can just write your h of n plus 1 this way. It is h of n shifted left by 1 unit, and then x of 0 is 1 times h of n. We already have the value for this. Again, it's always a good convention that we just keep the arrowheads aligned. Just to keep the arrowheads aligned, I will just write it like this. So either you can put a 0 here or you can start the bracket from here, it's up to you. So it is just to align your arrowhead. And plus x of 1, which is again 2. And this is this h of n shifted right. If you shift it right, it will become 1 1 0 1, but arrowhead will come right here. And it is always nice to just write it this way, where you have your arrowheads aligned 1 1 0 1, and you have an arrow right there. So if we just write it down here again, this thing will now become, although if you want to put zeros here, it's up to you. You want to keep lines, up to you. So these are what we get after just plugging in values. So we just rewrite them, taking 2 inside, it will become 2 2 0 and 2 with the arrowhead right here. The second one will become 0 1 1 0 1, arrowhead right here, and the third one will become 0 0 2 2 0 2 with the arrowhead right here. And if we add all of them together, you end up getting your answer, which is your y of n, and this will be equal to, this will be 2 3 3 4 1 and 2 with the arrowhead right there. Now we can just write it like that, or if you want to draw this, we can draw your y of n also. Your y of n, again, this will be the value, let's say 4 right here, and then we have value 3, then we have 3, then we have 2, and on this side we have, let's say 1, and we have 2. So this is 2 3 3 4 1 and 2. This is for index -1 0 1 2 -2 and -3. So y of n plotted would look something like this. Y of n written will look something like this. So this is a bit more, you can say, detailed example, where we are not limiting x of n or h of n on one side only. We are having a particular both-sided x of n and h of n. So you see that we have just plugged in values in the formula. The only major catch that you need to see, not one but two catches. First of all, what will be the limits for this k? So what will be the limits for this k, so that once we open up, what all terms are important for us. And next, once we just write all that terms, if you see the convention that I am following, you don't have to follow it this way. You can write it in a single line. You can write all this in a single line. All this in a single line is an answer. But if you write it this way, then addition of all these terms actually becomes more simpler. The alignment part and addition part becomes more simpler. Otherwise, if you had written it in a single line, if you had written all this in a single line, then visually seeing and adding the respective terms at times becomes cumbersome. So for those of you who are, you can say, good with these types of things, can just write it in a single line and still get this answer very nicely. But if you want to be more careful, then it always helps if you just write these types of things in multiple lines, so that the alignment part remains correct. So one thing is your this limits, that how do you put in the limits for k. The second thing is that once we have expanded all these terms, once we write all these terms, then how do we take care of proper alignment once we are adding all this? If you see this, these are like separate impulses which are added together. So if you see this, these are like separate impulses added together. So if we, let's say, want to draw this thing and this thing and this thing, so diagrammatically also we can draw these three and then add them together. Like if you take the first term, this first term would be something like this. This is your x of minus 1 h of n plus 1, this first term. It is 2, 2, 0 and 2, and the last 2 is right here. So 2, 0, and if we have 2 of these right here, so 2, 2, 0, 2. So this is the first one, starting from minus 3, minus 3, minus 2, minus 1, 0. And then if we draw the second set is 0, 1, 1, 0. So we have 0, and then we have 1, and then we have 1, and then we have 0, and then we have another one right here. So the indexing parts again the same, minus 3, minus 2, minus 1, 0 and 1. These are 1, 1 and 1. And the third term, if you see, it is basically, we have a 0, again a 0, then we have a 2 here, and then we have another 2 here, then we have a 0, and then we have another 2 here. So 2, 2 and 2. And this is for minus 3, minus 2, minus 1, 0, 1 and 2. So if we add all three up, it will be much nicer or easier to add them up if they are aligned. This 0 part is aligned, and that is what we have taken care right here also, that the 0 part is aligned. So if you align them, then adding becomes simple. It will be 2 here as a result, it will be 3 here as a, it will be here as a result, 4, 1 and 2. 2, 3, 3, 4, 1 and 2. And the answer, I don't have space right here, it will end up giving you something like this. So this addition, be careful with the addition part. So some people love to do everything graphically and they love to do it this way, and others are good with numbers, just keep the line like that and do it. Others are even more, you can say, confident. They just write everything on a single line, and in 3 lines they can give you an answer. But again, that way they have to be careful about the alignment part, that what gets added to what. So any questions here? A more complex example was solved right here, where x of n was given diagrammatically, h of n was given again diagrammatically, and the question was that if input is x of n this and your impulse response is this, what would be your y of n? And we just solved it mathematically and showed you it will be this. So this was the convolution part. Now, okay, I will just cover it here also. Till now we have covered convolution for this examples that we have covered. We assume that your x of n was also finite and your h of n was also finite. Both of them were having finite number of impulses. Now, what if your x of n or h of n had infinite number of impulses? How do we use the concept of convolution then? And again, this is what is shown in the example that you will see in a moment. And you're given x of n, you're given h of n. H of n is given to you as u of n. Remember that u of n, it is a step signal, unit step signal. So impulse response is a unit step signal, and this unit step signal, because it goes on and on and on all the way to infinity, so it will be a IIR, infinite impulse response. So this is u of n, and x of n is given to you as alpha raised to power of n u of n. Now this is the example that is given to you, that if we are given x of n this way and h of n this way, then what? So Let's just talk about the signals for a moment first. If we see this x of n, if we try to plot this x of n, this alpha, we are told that your alpha is less than 1. So this alpha raised to power of n un or a raised to power of n un, any constant raised to power of n un, this is a signal which is an infinite signal, and you will come across this type of a signal a lot later on in this course also, in DSP and other further signal processing areas. You will come across this type of signal a lot. So how does that look like? So x of n, if you have this alpha raised to power of n un. Now first let's take this example where alpha is less than 1. Let's consider alpha less than 1. It can be anything. Let's say it is 0.5 or any decimal value. Less than 1 means a decimal value. If it is magnitude part is a decimal. If it is a decimal value, then you will see that higher powers of decimal values always end up giving you a lower number. For example, alpha raised to power of 0 will give you 1. Alpha raised to power of 1 will give you 0.5. Alpha raised to power of 2 will give you 0.25. And similarly, you can go on and on and on, and it will keep giving you low numbers throughout. So this is something that we need to see. So something like that. As we see that as the powers is increasing, the value of your x of n is decreasing. If you plot it, you will see that it will start with 1 and then becomes 0.5 and then becomes 0.25, then becomes 0.125 and then becomes smaller, but it will keep going on and on. So this is your, and this is, you will see a decaying sort of situation. It will not become 0 ever, but it will become a very small value as the powers become very high. So this is sort of a decaying thing. So for alpha less than 1, a decimal value of alpha, for a decimal value of alpha, you will notice that this thing would be a decaying sort of a signal. It will be an infinite set of impulses, but it will be a decaying sort of a set of impulses. They will decay. The other, if alpha
Sir?
was, yes.
सर ये हमेशा exponentially decrease करेगा?
Typically, once we say exponential decay, this is this type, e raised to power of minus, let's say, a n. So this is exponential. This is power of exponent. So you will say that it will decay. It is not really an exponent, but it is a decay. So exponential decay is a very specialized sort of a decay where the decay slope follows that exponent. Exponent, you know, is a particular constant value. So I will not talk about that exponent right here. So it is very similar to that. It is going to decay and will tend to become very close to 0. But this is something different from exponential decay. It's a decay which is similar to that, but not really exponential. Exponential is a specific set of constant. So and specific set of pattern of decay also. So if we have alpha equal to 1, if alpha is equal to 1, it will end up becoming u of n. So constant throughout. 1, 1, 1, 1, 1, 1, 1, 1. It just remains 1. So this is for alpha equal to 1. It is basically constant value throughout, going all the way to infinity. And the third part is where your alpha is greater than 1. So if your alpha is greater than 1, let's say 1 point something, 2, 3, 4, anything, we know that higher powers, its square, cube, higher powers will end up increasing this number. In that case, again, alpha raised to power of 0 will still be 1, but you will see that it will just start increasing as we increase n. So it will be a sort of a increasing sort of a trend. So this is your x of n, which is your alpha raised to power of n un with alpha less than 1, equal to 1 or greater than 1. So if it is magnitude, I'm putting a magnitude sign here, although plus and minus will be oscillating, but if you take the magnitude part, it will be something like this. So for positive alphas, you will see it will be doing like this, and if your alpha is negative, it will be just oscillating plus and minus, but still decaying. Same goes here. For positive alpha, it will be just doing like this. For negative alpha, it will be alternate plus and minus, but pattern will be going that way. So this decaying or growing type of signal is something that you will come across a lot. So that was just talking about the signal. So in this example, we are given h of n and we are given x of n. This is your x of n, where we are given that your alpha is a decimal value, a positive decimal value. So you will see that we have a sort of a decaying sort of a situation. So this is your x of n, infinite set of impulses, and this is your h of n, which is just step signal, becomes 1 and remains 1 throughout. Now, how do we actually see? How much time we have? Do we have time to solve this example, or should we pen it for the next lecture? Go over this yourself, see whether you can judge how do we come to this and how do we come to this answer. And next time we'll start with this example. We'll continue from here.